Hello, Khalid.
Hello, Doctor.
Yeah, you're the first to attend. Oh, Luke is here. Yeah. There's no one in the class. Alia did say that she has one of her, or her son has a doctor's appointment, so she might not be able to make it.
I see.
So, and actually, Jordan also said he might not be here. Apparently, his grandmother has COVID. So
Oh,
that's not really.
yeah. Actually, 2 weeks ago, my sister and my uncle has caught the virus.
They had what? Tell it again.
They caught the virus. They got COVID-19.
Okay. So they
So
got.
it was kind of struggling here.
Yeah. Do
My
you
my
live?
my sister had. No, actually, we have separate homes here, but we were worried because the kind of everyone got infected from my sister, so we waited like 1 week or so to think to make sure that she was the only one to get it. So my sister has recovered from it, but my uncle is still struggling in the hospital.
I see.
Because he's like 80 years old, and
Oh, I see. Yeah, that's aged. Yeah. Okay.
it was a couple of days ago. Also, I've learned that my other uncle, she got it. So my aunt, I'm sorry,
Okay. Yeah.
she got it.
Yeah. Once it is in the family, then it is hard to contain it because most probably everyone interacts.
Yeah.
Yeah, it's just to be prepared for it. That's the only thing. Yeah. And at the same time, most probably we can all not avoid it. Will eventually hit us, I guess.
Yeah, and I remember back in like April or May, I listened to a specialist. He said that the the virus is kind of transmitted between people in a mysterious way, not the only ways that they told us about, but they still figuring it out.
Yeah.
And I believe that. Sometimes you take all the precautions, but it's still transmitting.
Yeah. It's hard. Yeah. Okay, so I think that's at least two of you. So who are the Moses usually comes. I think he comes to the class, so I'll be getting late. Who else? Moses, you. Who's the fifth one? Oh, Michael is out. He's not in the city. Okay. Okay, so wait, homework 7. Let's make them 3. Today I want to, oh, Michael, you're there. Good. Which state are you in now? Kansas too?
I'm in Kansas right now.
Good. The attendance from 2 countries and 2 states. Okay. Yeah. Today, I want to talk about analytic continuation, broadly called analytic continuation. It's a big topic. We'll do a very simple exercise, but hopefully I can convey the idea at least. So in the beginning, 5 minutes or so, I will convey the idea of what it means to analytically continue, and then do a specific example, again, a very simple example. So let's do the simple idea. So let's say we all know what is a factorial, right? This is a factorial function. Would you call it a function? Factorial, I guess. Yeah. So n factorial. That's right. N factorial is by definition n into n minus 1 into so on. You go until 1, right? You cannot go below that because then it becomes 0 and it will go to 0. And typically, it's understood that this has to be, n has to be a positive integer. N is positive integer. And due to that reason, it is, you never say, actually it's 0 factorial is okay, right? How do you define 0 factorial? Yeah, what is 0 factorial?
I think that's also defined by extending the pattern.
By the pattern?
Or like going beyond the pattern is what I mean.
Oh, going beyond the pattern. Yes, yes. So we do say that 0 factorial is 1, but it is not very obvious why that is the case, right? So that is actually already an example of why should that be 1. In fact, if you're aware, you even talk about 0.5 factorial, right? If you look up literature, however, let's say, just to, if you're not aware of it, however, it is okay to define 0.5 factorial. Right? What is this? And what is 0.5 factorial like that? Anyone is aware of? It's square root of pi. I think so. Just check on this. Okay, extra credit, right? Check on this. Extra credit. Check this. But then that immediately raises, how do you even think of what does it mean to say 0.5 factorial when clearly on the top line, I said n is a positive integer, so does it even mean anything? And is this correct or not? And we will say that, oh, this is actually language-wise, it's wrong. You never say 0.5 factorial in this sense, but analytic continuation of n factorial has a meaning. So what does that mean? So the way you would say that is find a gamma function. So this is factorial, that's what it is. Now gamma function is defined as the gamma of, let's call it S. And Moses, you're across the internet today. Yeah.
Yeah.
Yeah, we have everyone.
Woke up late today, and then the internet at my apartment hasn't been working, so I'm joining on my phone.
Yeah. Okay. We at least have some attendance. Yeah. The first few minutes. Yeah. Okay. So I was saying we're doing analytic continuation. The function we're talking about is factorial. We all understand that factorial is 3 factorial is how much, 5 factorial is how much. but sometimes you might encounter situations where you will read 0.5 factorial is equal to something. I think it is square root of pi. It's an extra credit for you to check. But what does it mean? And I'm going to say, yeah, there's a sloppiness in doing this, but what do you exactly mean by by saying? So that's factorial. There is another function, gamma function. It is defined as, this is defined as an integral. This is 0 to infinity, and it is dt over t, and then t raised to s. You can also write t raised to s minus 1, cancel out one of the factors, that's perfectly fine, and e raised to minus t. Okay. And it turns out this has like we have a condition on this, right? When you do this to define this function and factorial, n has to be a positive integer. If you go beyond that, it might not make sense, or it might not be, or the how you evaluate those directions may not be sufficient. Similarly, here there is a condition on s, and the condition is that real part of s, we are saying that s could be complex. The moment I say real part of s could be complex, and real part of s has to be greater than 0. So that's a condition you put it. You can generalize this further to a complex, to not restrict it to real part of s greater than 0, but let's not do that there. But what do we mean by what's the connection between gamma function and factorial? It turns out that if you were to actually evaluate this for, maybe we can try that. Yeah, so let's try to evaluate this for gamma of s can be any positive complex, or what do you say? So complex number on the right half of the complex plane, and let's say gamma of n, right? Where n is a number now. When I write n, it could be gamma of 3, for example. So that's equal to 0 to infinity, and you immediately say that this is t raised to, let's do 1, right? 1 will be easy, t squared. Yeah. Let's do 1, right? Gamma of 1. I don't know. I think gamma of 1 is n minus 1 factorial. So, okay. So that gives you dtt, and that's e raised to minus t. That's equal to how much? That's just 1, right? That's easy. What is gamma of 2? That's equal to 0 to infinity, and dt times t of exponential of minus t. And probably we can do this, right? So I can say, I can put in a lambda there. So this is equal to 0 to infinity. There might be other ways of doing this. This is e raised to minus lambda t. And I have to set lambda equal to 1. Set lambda equal to 1. Limit lambda tends to 1. That's one way of doing that. Then I can say this is the same as limit lambda tends to 1 of minus d by d lambda of 0 to infinity of dt of e raised to minus lambda t. When you integrate that, you get a minus 1 over lambda, right? So this is equal to minus d by d lambda of 1 over lambda. And that's how much? Out here, 1 over lambda square, correct? Minus 1 over lambda square. And that's again 1. Correct? Let's keep doing this for a minute. Let's now do general. I think now we can do this very generally. So gamma of n for positive integer. Do the same trick and you get limit lambda tends to 1 of 0 to infinity dt t raised to n minus 1 this time, right, and e raised to minus lambda t, which is the same as minus d by d lambda raised to n minus 1. Every time I take a derivative, it brings down t, and that's 0 to infinity dt e raised to minus lambda t. I'm just demonstrating something. This is, I was not planning to do this. So this is minus d by d lambda raised to n minus 1, 1 over lambda again. Correct? But now there are n derivatives. In the first derivative, I get a 1, right? In the second derivative, I get a 2. In the third derivative, I get a 3, and so on. So, is that correct? So, what's the last one? First one, I got a 1. Second one, I got a 2. N minus 1, I got an n minus 1. Which is n minus 1 factorial. Right. So, forget the details in there. What we have shown is that this gamma function, gamma of s, is equal to s minus 1 factorial if s is a positive integer. But of course, this function is not just defined on the positive points. So what we have shown is that there is 1, 2, 3, 4. If you evaluate this function at these points, it actually evaluates the factorial, but this function is defined everywhere on this, on the right hand side of the complex plane. So in that sense, and if this is a unique way of reaching here, now it's possible that if you reach from right hand side, left hand side, it gives you different limits, then that's not a good idea. But if it's a unique way of reaching there, you say that this is an analytic continuation of the factorial function is the gamma function. Okay? Because that if it is a unique way of reaching those points. And that's what we would mean by analytic continuation. Now there is also, now that this is not the complete story, right? We have left out half of the complex plane. So you would like to analytic continue on this side also. And that's also possible. Gamma function, this expression for gamma function is not the complete story. That is a full story. And usually you go into the complex plane, you have to make dz over z, and you have to put a contour integral there. We won't do that. But instead, we will talk about the basic integral that's necessary to go from this half of the complex plane to the next half. Okay, how do you do such a thing? And it's the same idea again. It should be, the value of the function should be the same on the region that we already know. And there should be a unique way of reaching there. Whenever there is a discontinuity there, it should be a unique way of coming in there. It doesn't matter whether you come in from this region, it should all be a unique way of reaching there. And if it's an analytic function, we know that that is a unique structure there, right? If we say that its derivatives are defined, that means the whole function is defined. In that sense, if we can get one extension from this to that, that is the only extension, and we say that's an analytic continuation of this function. We won't talk about gamma function, but instead we will drop this exponential and talk about what that function is and analytically continue from this to from the right plane, right half of the complex plane to the left half. Any questions at this stage? And at least the motivation part, is that clear? What we mean? Okay, so okay. So the function we will talk about, so let's say, let's define some functions, right? So mu of 0, these are all the same functions, but this is mu of s is 1 over s. Cannot be a function simpler than that, right? It's still not the simplest in the sense it is having a, like at s equal to 0, it's not well defined, right? But and s is complex, right? So this is s is so everywhere. So this is well defined everywhere except s 0, right? So and s is complex. Remember, s is complex. Okay. Let's define mu1 of s to be equal to, mu1 of s is, let's say, 0 to infinity dt. It can be written as t raised to s minus 1, but I like to write it as dt over t times t raised to s. It's of course dt times t raised to s minus 1. Okay. And what is that integral? Can you evaluate that integral quickly? Can you guys evaluate that integral quickly? Can you guys evaluate that?
Is it just s minus 1 times t to the s?
Try it, but there are limits, right? Yeah, there are limits, right? Evaluate.
Oh,
the,
yeah.
Okay. That's correct. Yeah. Like, it's not a tricky question, just simple integral. And what is that? What is the answer? What is bothering?
Is it infinity?
Why? No, right? What are you evaluating it? Okay, so this is equal to t raised to s minus 1. So t raised to s minus 1 plus 1, so that's t raised to s, correct?
Mm-hmm.
Over s. Agree? And divided by, evaluate this at t equal to infinity. Right? Oh, why is that at t equal to infinity? Oh, is that what is bothering you guys? Oh, help. What happened? Help. S is greater than, oh, yeah. Okay, yeah. T equal to infinity and t equal to 0, correct? Oh, yeah, that's not what I meant. Sorry. Yeah, that's correct. That's wrong, right? It's divergent. That's why you guys are not answering me. I was thinking what's going wrong because I gave a wrong integral. Okay. Let me correct this a little. Sorry. And that is go from 0 to 1. Much better, probably. Sorry about that. Good that I didn't lose my patience and I scolded you guys a lot. Oh, you guys don't know how to do an integral. And then I realized that I gave the wrong integral. Okay, can we do that now? Sorry for that.
One over S.
1 over S, right? Thank you. So that's 1 over S. Right, right? That seems like both are the same. Correct? That's nice. So it seems like, oh, good. We have a, so this will be called, and so this is called often, or mu1. So in this sense, mu1S is an integral representation of mu0 of S. Right? Usually you don't differentiate mu0 and mu1. You say it is the same, but its domain of where it is satisfied is different. And in fact, we are going to analytically continue this. We'll wait for that. And notice that this function is very much the same as gamma function, except for the exponential. So it's the same tricks that is used for analytically continuing gamma function also. Exactly the same, because its problem is this. Now, okay, so this seems like these two are the same on the right hand side, but are they really? So let us calculate mu1 of 1. What is mu1 of 1? Don't use this, okay? Gotta use the integral. Okay, don't immediately go to the right hand side and do that. So if we were to evaluate this, this seems like 0 to 1 dt over t and t. That seems to be okay. So that's 1 if I were to put it on mu naught of S, so that's equal to mu naught of 1. Great, that's good. So that seems to be fine. Now let's do mu1. And of course, mu1 of 0, we know that that will be a problem, right? Because that's not well defined in even the first one. So 0 to 1 dt over t. That's a problem already, right? What's this integral? That's log of t. Evaluate this at 0 and 1. That's minus log of 0. We can best say is that limit is minus of limit delta tends to 0, right? That blows up infinity, right? This is 0 will be negative infinity, so it is plus infinity, right? It surely is not well defined. But then you would say, oh, I don't care about that, because even my original function to begin with was not well defined at 0. So let's try mu1 of minus 1. And you will see that that's the same problem, right? Now we have 0 to 1 dt over t squared, right? And this is what? Minus 2 over t cubed. And then we have t equal to 1, t equal to 0. T equal to 1, this is well defined, but this again blows up. Right? This again goes to infinity. Not of the same kind, one goes up as quadratic infinity, and the other is logarithmic infinity. So then we would like to know, so which means to say that this integral is not always true. Mu naught is well defined, but mu1 on the left hand side, the integral representation is not really equal to this. Its integral collapses. That's the definition is collapsing. It's not the answer that is a problem. The way you do it is the problem. So you have to put a condition in here. Right. This, when I say that is this equal to this is true only for real part of S greater than 0. Same problem as gamma function. Like S could be complex also, and you have the same issue, because the moment its real power goes to left, it has this power issues. The moment, because the integral is is not goes to infinity at that limits. So that's the restriction there, right? So let me remove this. This was just elaboration on that, correct? So again, remember your complex plane, and this is the complex S plane. This is defined here, but not on the left-hand side. But we know this is a very simple example in the sense that we know that this is equal to, this is supposed to be equal to 1 over S. So we can do better, like it should be possible to do better than this. So, before I proceed, this will be called an analytic continuation of 1 over S, mu1, or how do you say this? Mu naught of S, if you can achieve that, will be an analytic continuation of mu1 of S. Okay. In this case, it is a slightly misleading because that's the total function, right? You know exactly what that is. Often, you don't know how to do an integral, so you don't know what that exact is. Right? So you can only get better and better in your region. So here, this is our region, we know this, but we would like to continue this to the right half plane. And for that purpose, let me define mu2 of S, which will be actually mu1 of S. We will show that this is actually equal to mu1 of S. It's the exact thing possible. And in that sense, this will be the true analytic continuation. So I had to analytically continue. So I had to come up with a function. So this requires a lot of thought, experience. So let me just propose that this is now not being done on a real line. This is now on a complex plane. This is dZz and t raised to z. Seems like exactly the same function, but now t is not real. This is on a contour. So this is on a complex plane. Notice this is a z-s plane. Now I'm talking about a z plane. So do not confuse between the two. So this integral happens in a plane, but it is even, oh, where is my s? Oh, what did I say? Oh, this is all messed up, sorry. Z raised to s. Sorry. Like all the t's I replaced with z and s I kept it as it is. So there are two parameters in principle, z and s, but notice that z is integrated out. So the function does not depend on z. So this function is actually dependent on s. I'm continuing in s, but I have to perform the integral in a plane, and that's the z plane. And that's where the contour is. And that contour, I select it to be. So this point here is z equal to 1. I choose my contour, it should be like this. And that's it. It's not a closed contour. Notice that till now, whatever we have done, we have always got a closed contour. And the idea was to use Cauchy's theorem. And we will need that, but since this is an analytic continuation of gamma function, this is related to analytic continuation of gamma function, eventually we would like to extend this all the way to infinity also. We won't be doing that here, so that's why we don't close it. So for our purposes, we just need this. So we won't be using Cauchy's theorem because it's not a closed contour. Okay, so let's label this. Let's call this C1. This is C2. This is C3. And our contour C here is C1 plus C2 plus C3. And the claim is that if you evaluate this on this contour, you will get exactly 1 over s. Okay, no issues, no restrictions on z being greater than 0 or s being greater than 0 and so on. And once you do that, then we can immediately say, oh, so this is an analytic continuation of mu1. So that's our goal. So our a problem has reduced to showing that this actually is 1 over S. And it's a little intricate. It doesn't show up very easily, but each step is really tiny. It's just that at all the infinities, there are infinities coming from each part of the contour, and eventually all of them cancel out. So there's a lot of fine cancellations happening, but very easy to see, very clearly visible. So let's see this. So let's calculate C1. First of all, we need some parameters, right? We just need, let's say this is epsilon, right? The radius of this is epsilon, right? Of the circle is epsilon. Yeah, as we go, we'll define that. Okay. So integral of along C1 of dz over z times z raised to s. Oh, before I proceed anywhere, I should say this has a pole, right? Sorry, this has a branch line. Because this is raised to power s, this could be 1 over 2, 1 over 3, 1 over 5, I don't know what. Like, and whenever there are fractional powers, this will in general have a branch cut. Right? Yesterday we did, or in the last class we did z raised to half. So in general, there is a branch cut, and that branch cut is actually along this line. Okay. So that is sort of important or useful in the sense, otherwise C1 and C3 will simply cancel, right? If there was no branch cut, then both will cancel out, because if it is continuous, the value of the function below and up will be the same. But if it is discontinuous, then there is a chance that you can get something out of it. Okay, so calculate on C1. What do I substitute on the bottom half of the plane? So I go from, let's say, is theta I haven't used anywhere. So I would say, let me substitute z is equal to epsilon. No, here it is on the real line, right? So it is x times e raised to I, and I go from 2 pi minus delta. And yesterday, maybe I made a wrong comment. Yesterday, I was doing a similar thing. And Luke, it was you who pointed out that, oh, what about multiplicities associated with this? Notice that we are going, when I go from here to there along a circle, I only go from one circle. Only when I go multiple circles, that's what there is that n has a meaning, but it is not the arbitrariness that is there. But if I actually go from here to there, it's only one, and e is one in that case. But there is a choice for me to go double the time. And in fact, there are cases when you have to do that. If you look up, yeah, so this is a good extra credit, right? Yeah, it's not very much discussed in textbooks. So this is extra credit. Look up, I think it's called Pokemore, P-O-C-H-E. Pokemore, I might be, spelling might be wrong. Pokemore, just look up, like Google kind of senses it anyway. It's called the Pokemore contour. And it is in the context of beta function. The analytic continuation of beta function involves what is called Pokemore contour. And that contour is not just straightforward, you go multiple times. Sometimes you have to go multiple times just to get rid of the discontinuity. So once you go, you pick up a discontinuity. Second time you go around another pole, you cancel that discontinuity. So sometimes it is useful to go multiple times. So that was just a small comment related to what I said yesterday. So here we are going, theta is going from 0 to 2 pi. So I pick up the bottom value, and delta, I want to take the limit delta tends to 0. This can be written as x minus ix delta, right? Or x, well, yeah, x plus x I times x2 pi delta. Is that right? What am I doing? What am I doing? Help. It's in the small limit. Yeah, forget it. Yeah, this is good enough. Right. Okay. So substitute that in here. So I'm going also dz, right? So dz is equal to dx. X is the variable. E raised to I 2 pi minus delta. So the limit goes from 1, that's the extreme right, and I go all the way till here, right? So remember that, so there is a radius for this, and that's epsilon. So how far do I go? I don't go all the way to 0, I have to go epsilon. So the limit, so this, the radius of this contour C2 shows up in C1. So its limit is from 1 to the radius of this epsilon, and how much you're shifted, that's going in the limit delta tends to 0. So here, there are two limits being taken. So limit delta tends to 0 and epsilon tends to 0. So that compresses it. And dx e raised to I 2 pi minus delta, and then z is x times e raised to I 2 pi minus delta. That will cancel out, and z itself is x times e raised to I 2 pi minus delta raised to s. Okay. Let me copy this here. So this is z equal to x e raised to I 2 pi minus delta. So that's a substitution. That I have more space. These two cancel out. So what I have here is, let's see, I have e raised to I 2 pi s that can come out. And so this is all, I guess, yeah, so e raised to I 2 pi s. And there is limit, delta limit I can take, there is epsilon that remains. So that's 1 to epsilon. 1 to epsilon, and then there is dx. X raised to s, and there is a denominator x, so that's x raised to s minus 1. And that's equal to e raised to I 2 pi s times, what is this? This is x raised to s over s, I suppose. Right? So x has to be substituted. So this is epsilon raised to s. And when x is equal to 1, that's just 1 minus 1 divided by s. It is clear that if s was greater than 0, if real part of s is greater than 0, then this is of course 0. That's what we are good with that. But we want to do more than that. If s, real part of s is less than 0, this is 1 over an epsilon, and this can lead to infinity. That's our problem. Right? So this is the divergent case. So this is divergent for a real part of s less than or equal to 0. Equal to 0 seems to be okay. So less than 0. Right? Is that right? And so it seems like one might give up here when you're attempting for the first time. Oh, I did save my divergence just like going around, but let's wait. I mean, because this is going till here, right? There are more pieces to that. So all these divergences are going to cancel out very nicely. So let's now do C3, right? There are three contours. This is C3, dz over z, e raised to s. Very similar. Now so this is on C1, I substituted this. On C3, I substitute z equal to x times e raised to I delta. It's slightly above. So that's the contour. That's the substitution I make for C3. And then I'm going from epsilon to 1. Again, there is a limit. Delta tends to 0 and epsilon tends to 0. And this is dx e raised to I delta. This will be again x times e raised to I delta. And you have x times e raised to I delta raised to s. And now notice there is e raised to is delta, but I'm taking the limit delta tends to 0, that goes away. So that's equal to just 1. So this is 1 times limit epsilon tends to, oh, this is not infinity, that is 0. Sorry about that. That's 0. And do the same thing. Right? This time we're going from epsilon to 1 and dx x raised to s minus 1. And that is just 1 times, so this is 1 minus epsilon raised to s over s. Again, there is a divergent piece, but now you see that, oh, there is a hope there, right? Oh, so that cancellation might be possible, right, between the two. But there is an exponential I2 pi s showing up on that piece. So that's not rightly there, right? The cancellation is not really there because the coefficients are not there. Coefficients are not the same. So at this point, you might really give up, but then there is one more contour, right? So go through the whole thing. So C2 dz over z times e raised to s. This time we substitute in C2. This is now on a circle. So we say this is epsilon is constant and e raised to I theta. So that's our substitution. So that's on C2. We are going in the opposite sense of the contour, but that doesn't matter because we are not using Cauchy's theorem. But there is a limit, epsilon tends to infinity. The limiting cases for this contour is you start from 2 pi and you go to 0. And dz is, take the derivative in there, so it is I epsilon e raised to I theta d theta, that's a dz over z, which is epsilon e raised to I theta. And z raised to s, it is epsilon e raised to I theta times, or raised to s. And the epsilon e raised to I cancels out. Take the limit, epsilon tends to 0. So this integral is equal to I times epsilon raised to s, right? I times epsilon raised to s, and then we have to take, limit, right? So limit epsilon tends to 0. And we have an integral 0 to, epsilon s minus 1 apparently, correct? No, epsilon cancels out. Yeah. So this is, I can Yeah, 0. I can make it 0 to 2 pi and put in a minus 1 there. 0 to 2 pi d theta and e raised to I s theta. What is that integral equal to? Just that 0 to 2 pi d theta e raised to I s theta. A little careful, otherwise it's elementary. So the question is, so what is this integral equal to, right? 0 to 2 pi d theta e raised to I theta, and you can write s anyway. So this is a function of s if you want, right? F of s. Yeah. What is that equal to? Remember, exponentials are nothing but cosine theta plus sine theta if you want.
Zero.
Yeah, it is 0, right? It is 0. Right? It's 0 because cosine functions are periodic and 2 theta. Except there is one small catch. What happens when s is equal to 0? This is correct answer when s is not equal to 0. What about s equal to 0? Oh, is it, by the way, is that correct? Is it right theta s? Did I say this correct? Is it 0? I theta I 2 pi s. Yeah, there is actually some, yeah. 2 pi s. Yeah, let's do that integral properly again. It is 0 actually most of the time, but let's be careful, right? I think it's on second thought I'm a little worried. This is e raised to I theta s over, I'm doing with theta, right? So this is e raised to is evaluated at 2 pi theta equal to 2 pi and 0, right? Theta equal to 0. So this is e raised to I 2 pi s. When s theta is equal to 0, it is 1, right? Minus 1 over I. And when s is equal to an integer, then it is 0. Right? So that's what Michael, you were saying. So yeah, you can capture most of it. So let's say this is equal to, yeah, this is what is needed actually. So 2 pi s minus 1 over I times, is that an s? Yeah, 5 times s. Correct? Is that right, Michael? Did I do that right? Satisfactory or not? So again, I just did a simple integral, right? So this is e raised to I theta s over is evaluated at theta equal to 2 pi and theta equal to 0. When I evaluate at 2 pi, I get this, then 0 it is 1, and is common, correct? This is when s is not equal to 0. Agreed? What about s equal to 0?
Two pi.
2 pi.
2 pi. Right? So it is 2 pi. That's 2 pi. Agreed? Okay, so we do know that s equal to 0, the primary function, has a problem, since we are aware of that. Otherwise, you have to take these two cases. Let's restrict our analysis to s not equal to 0. So for s not equal to 0, I can write this is equal to limit epsilon tends to 0. There's a minus I epsilon raised to s, and this is 2e raised to I 2 pi s minus 1 divided by s, or I times s, right? Which is the same as, cancel the i's, and I can write this as 1 minus, can I write something better? Right? Yeah, let me write that in a second. I cancels out minus and a minus, that's 1. So that is epsilon raised to s. I'm trying to write it in the best way possible. This. I think that's all. And s is not equal to 0. You have restricted my in that analysis. Hopefully I didn't confuse. So mu2 of s, if I were to add up all this, if I add up all these three pieces, I get, so I get limit epsilon tends to infinity, tend to 0 is there in all three. So that's e raised to I 2 pi s times epsilon s minus 1 over s. That's the first contribution. The second is 1 minus epsilon s over s. That's the second contribution. And third contribution, we get epsilon s 2, 3. Now I'm missing something. Maybe not. Epsilon, that 1 minus e raised to No, that's okay. Yeah. It's not clear that where the cancellations happen. Surely if there is S that is common, let's try to cancel out whatever is canceling. Notice each one of this, there is a lot of divergences here. For epsilon tends to 0, if S is negative, then it can be divergent. But there are cancellations clearly. One is this piece, cancels this. And this piece cancels the first piece. Right? And you clearly see that the epsilon tends to divergence cancels out. And whatever is left, hopefully, is meaningful. And that's equal to now epsilon is gone. So whatever is left is e raised to I. There is a 1 left out, and there is a 1 minus e raised to I 2 pi s over s. That is not really 1 over s, but it's not bad. You just have to divide that out, right? To take it onto the left-hand side. So if I were to define my mu to s, I should have been looking forward to this. So mu 2s, mu 2 prime s, is equal to let's say e mu 2 of s divided by 1 minus exponential of I 2 pi s. Correct? And this is exactly equal to 1 over s. So mu 2 prime as an integral is equal to 1 over 1 minus e raised to I 2 pi s times contour integral along that contour that I said, z over z times z raised to s, which is exactly equal to 1 over s. And if you evaluate this, and this is valid, so this is everywhere on z, all s not equal to 0. That's the only condition you put. It might seem that when you look at this integral, and this is the same thing that happens when you do look at an integral representation of gamma function or zeta function, oh, this integral is not very well defined, and whenever this becomes 1, right, this seems like it blows up, right? But that's misleading because, as I showed, this integral gives you that factor. Like whenever you evaluate that integral, you will get that factor, and that is supposed to cancel that. So when you look at it right on the face, it seems like there is an issue there at s whenever that becomes 0, but that's not a problem. And this is true for all. You will see expressions for gamma function, zeta function. They will have this sitting in front of it, but that is supposed to cancel out whenever you evaluate it. So the point here is mu2. So the final point is that mu2 prime s is analytic continuation, is an analytic continuation because you can have many, right? At each point, they will always give you the same value, but in different regions, you can have different formulations. It's an analytic continuation of mu1 s. Mu naught is, of course, the exact function itself, so that's not very useful. So hopefully this gives you a feel for what analytic continuation is. And even though it is a simple example, this is the building block of gamma functions and beta functions and zeta functions. this one piece is what is used in everywhere. That is all I have. Thank you.
Thank you.
Yeah. So do you have to go places, Michael?
Yeah.
Is it?
Yeah. Tomorrow we're going up to the venue and we're doing our rehearsal tomorrow morning. And it's going to be a few hours and setting the place up and decorating and things like that. So I'm going to be busy all day tomorrow.
Yeah. So we don't have to look. Don't come to the class.
Okay. I was about to say I was planning on attending class, but I might not be there tomorrow.
Yeah. I think enjoy probably. And later on you can come and I don't want to misguide you, but if it is possible, then maybe you'll see the lectures later. Yeah. Catching up always, everything is at a price. So you have to do more work later.
Exactly. Yeah.
Yeah, and good.
I'll just say I spent the first 2 weeks of last semester in India, and I just kind of, I mean, I had to catch up quite a bit when I got back. I mean, Jordan was actually sending me the lecture notes, and yeah, then there were the YouTube videos as well. So I wasn't completely, out of it, but it was possible. It was possible for me to catch up and not really pay much attention for a couple of weeks. So I think you'll be fine.
That's reassuring.
When you started the conversation, I thought you attended a wedding in India.
Well, I did actually, but they weren't like actual Indian weddings. They were some weddings at the ashram, but they were very austere compared to how Indian weddings can be. So yeah.
Any wedding for that matter is a big event. Lots of things happen.
Mm-hmm.
Okay, so I think we finished contour complex analysis with this, and we'll start what is called Green's function next time. Like they're basically differential equations, but I'll introduce differential equation in the context of Green's function. So the point is, there are two kinds of differential equations. One is homogeneous differential equation, and one is inhomogeneous differential equation. So think of Maxwell's equation, the Gauss's law. If you set no charge, that's one differential equation. If you set there is a charge, that's inhomogeneous. Homogeneous will be when there is no charge. Inhomogeneous will be there is charge there. And inhomogeneous depends on the homogeneous, of course. And that's the idea of Green's function. So we will do inhomogeneous differential equation mostly. But we will have to introduce homogeneous for that. So we'll do some few simple exercises. So we have about 5 weeks. So we should be able to at least get the idea conveyed. Very similar to this, like we did not at all do analytic continuation, but we could get the basic idea out, which is from there, if someone motivated, you can build on that. So same thing, we'll introduce the basic idea of Green's functions, which will allow you in principle to solve any inhomogeneous differential equation. By any means, if you know the solutions for the homogeneous part. So let's do that next time. That's all. Okay. Bye.
Bye, guys.
All right. Hey, I had one question actually about the EMT take-home exam. With the math methods midterm, you allowed us to consult with each other.
Yeah, sure.
on that last problem?
Yes,
I
you
don't
can.
know.
You
Okay.
can consult in electromagnetism also. Usually that's the part of the in-class exam where I make a reasonable amount of assessment in there.
Hmm.
So that went fine from my perspective, but the only problem is that it was a very big disaster in the sense everyone failed in that. So I had to be very lenient in that. So that's okay. But otherwise, like as far as assessment goes, I did do that in the class. So the rest of it is to make the exam challenging.
Hmm.
So it's almost like qualifier. If you think of PhD,
Yeah.
usually qualifier is from undergraduate physics, right? But that is not a representation of what you learned. But for me, even that I'm able to assess. But then afterwards, I just have to make it challenging enough so that it's a master's level course. So the take home part is a master's level, and the other part I would say it's not undergraduate level, but at the same time, it's a simpler version.
Yeah.
But yeah, again, I don't want people to get discouraged even with that. But surely they should question themselves that, okay, we have a lot of things to do. Yeah, so that's the way to assess. Does that help? And I intend to get the curved grades out tomorrow before the class.
Okay.
Grade everything and actually, because I need the final exams also, but to a certain extent, all the grades to be updated, let's say. I won't be able to get the final ones because I won't get the grades from you, right? You see what I'm saying? Because the take-home part is necessary for curving.
Yeah. Okay.
I cannot do that before that. Yeah. But I intend to get it updated as much as possible. I'm a little behind in all the courses. And thank you, Moses, for
Me
grading
too.
the 2 or 3. You too,
Oh yeah. Yeah, for sure.
But thank you for doing that on time. Yeah. So today there is another
problem.
one.
Yeah, I noticed.
Thanks.
Yeah.
Hopefully before that I can finish off my grading. There's extra credit that I have to do there also. Yeah.
Hmm.
Okay. Are you TAing? You must be TAing, right, Luke?
Yeah. Yeah, I TA 2 lab sections of the 253.
Okay. Good. Okay. I'll let you guys go.
Yep.
Enjoy.
All right. Thank you.
Bye. Mhm.